Hi, everyone. Welcome to tonight's interactive stargazing event. My name is Hannah. I am a public program educator with Lowell, and I'm also a research assistant at Lowell. Tonight, we have a lot of exciting things planned to talk about, so I'm super excited to get started with everything. But real quick, I'm going to introduce you guys to the plaza tonight. So right now we are at the GODO, or the GeoVol Open Deck Observatory, and we have 6 telescopes that are ready to look through. But tonight we're going to be using one special telescope called our Plane Wave Telescope. And our plane wave telescope is super cool. It has a camera that's actually attached to the back where the eyepiece would be, and it can take pictures and exposures of these really, really cool deep space objects that normally our eyes wouldn't be able to see. But if you guys ever want the chance to come over to Flagstaff and check out Lowell and the cool telescopes we do have our premium access programs available now to book online at lowell.edu. Feel free to head over there and check out some of the programs we have. We have some for the Open Deck Observatory, we have some for the Clark, and we actually have some now for the Dyer Telescope. So those are super cool programs. I work some of them, and all my fellow coworkers work them, and there's really cool programs that I highly recommend checking out. And also something else I would like to bring up is that this month is the Mars opposition. So after this interactive stargazing event, for the next 4 weeks, we're going to be having live streams about the Mars opposition, talking about the history of the observations of Mars, talking about recent research that's going on Mars, and those will be starting at 8 p.m. instead of 8:30. So definitely tune in to check those out as well. And so with that in mind, let's start off with our first few objects tonight. I plan to talk a little bit about planetary nebulas. And so our first planetary nebula that we're going to look at tonight is going to be NGC 6781. And so a little bit about planetary nebulas so you get a better understanding of these objects. Planetary nebulas are these kind of rounder looking objects that are made of gas. And so this gas actually forms when stars die. And so stars actually have their own life cycles. They're born in clouds of gas, they form, they live their lives, and then they die. And when they die, sometimes they go out with a bang, and sometimes they just kind of fizzle out. And so planetary nebulas are the death of these smaller sized stars that are actually under 3 solar masses. So how we kind of measure the mass of stars is based off of our own sun. So we say, okay, our sun is around 1 solar mass. And based off that, we say, okay, other stars are 3 solar masses, or sometimes they're 100 solar masses. And planetary nebulas form when they're under 3 solar masses. And so a star will be having nuclear reaction going on in its core, and eventually that reaction will run out. It will run out of fuel to keep the star alive. And so when that happens, hydrogen and helium stop forming in the core. And then we start getting heavier elements. We get like carbon and oxygen, and those are the necessities that we actually need for life. And so when that happens, the gravity that's holding that star together actually kind of loses its balance, and it starts to swell up. And so when these smaller sized stars swell up, they get a little bit bigger, and they get bigger and bigger, and then they turn into red giants. And then these red giant stars are fusing heavier elements now in the core. And when these heavier elements are forming, that gravity is still unstable. So the outer shells of these stars will start to drift off, and it'll push out some of the gas, and we will get these little shells and rings of gas. And eventually all these outer layers will be pushed off, and that's when we're left with a planetary nebula. And so you can see right now on the screen, we have NGC 6781. And we got all these really pretty colors, and you can barely see it, but right in the center of the view is a tiny star, and that star is called a white dwarf. And that is actually the core of this dead star. That's the leftover remnants, and it has no nuclear fusion going on. And what will eventually happen is the star will kind of cool down, and it will cease to have any light emitting from it. And it will turn into a brown dwarf or a black dwarf, and it will be very cool, kind of like a planet. And so the whole reason why we can see these planetary nebulas is because of the light that's being emitted from these white dwarfs. So it's lighting up all that gas and it's making it look super, super pretty. And so this nebula in particular is in Aquila. It doesn't have a fancy name like the Ring Nebula or the Dumbbell Nebula, but it kind of looks like one of the more popular objects in the sky, the Ring Nebula. And so, like I said, it's in the constellation Aquila. It's approximately 2 light years across. And so some of the colors that you'll see in there, we got like a blue color, and that's actually some ionized helium. We have some cyan colors, and that is the glow of hydrogen and oxygen. And then the red kind of color is from nitrogen and sulfur. And so those were all in the star, and they get pushed out into our galaxy. And then eventually those gases could potentially make other stars, and then the whole entire cycle starts again. And so I like this object. It's a very new object that we just started looking at. It's not new in the sense that it was just discovered, but we recently just started looking at it, and I think it's a very, very unique object, and it mimics its friend, the Ring Nebula. And so we'll look at the Ring Nebula just a little bit later, but I want to look at some smaller planetary nebulas just so you can see the difference and the variation that we can get in these planetary nebulas. So the next one, let's try the Box Nebula. And so we have my boss, Sarah. She is actually working the plane wave right now. So you can see she pulled up the software that actually has a picture of the whole entire sky. And so you can see all the different constellations and all the different objects. And so all she has to do is type in Box Nebula or its catalog number, and the telescope knows to go to this object, and then we can take our picture. And so to the left, you can see she's like stopping and changing these numbers. And what she's doing is she's actually taking exposures of these objects. And so the whole reason why we can see these objects with the camera is because of these exposures. So the camera is soaking up around, she has 10 seconds of light right there. And so we have 10 seconds of light soaking into the camera to reveal this object. And our eyes doesn't stare at an object and soak up 10 seconds of light. It sees it instantly. So a lot of these objects we aren't able to see very well with the naked eye. But that's what's so cool about having this technology, is that we can actually see what's out there that our eyes aren't able to see. And so now she has a really, really good view of the Box Nebula. And so the Box Nebula is a very unique planetary nebula because it's called a quadrupolar planetary nebula. And so instead of it being kind of circular and having those shells that are pushed out in a very spherical shape, this one actually was pushed out in 4 different directions. And so that's why it's called quadrupolar. And so you can kind of see that there is some boxy shape in this nebula. And again, we have that nice, pretty blue color, and that's due to helium that was in that star. And we can't really see the white dwarf anymore in this star. It's just so bright. But yeah, so I think we have a question here from Daniel asking, why is the Box Nebula called so? And so I believe the Box Nebula is called the Box Nebula just because when you actually look at it through Hubble or some stronger telescopes, it's in the shape of a box. And so again, it's a quadrupolar planetary nebula. So we got those 4 sides, and so it strongly resembles a box. But there's no really scientific reasoning behind a lot of these names. It's just based off of how the objects look. So this one looks like a box, so they called it a box. All right, so let's move to another little planetary nebula. Let's move to the blue Snowball. So this one's NGC 7662. And so you'll notice sometimes with these objects, they have a catalog number. They'll have like some letters and numbers mixed in instead of like a basic name like the Box Nebula. And so the reason why that is that's because it has a catalog number. So we have 2 different catalogs that we mainly use at Lowell, but there's all these different catalogs that astronomers use to identify objects. So the ones we use are NGC and Messier. And so the different catalogs represent just different objects that were discovered in different time periods. And so the NGC catalog has thousands and thousands of objects in it, some planetary nebulas, some stars, some galaxies, just thousands of different objects, while Messier the Messier catalog is a shorter catalog. It has around 100 objects, and that was actually discovered by a person called Charles Messier. He was a comet hunter, and he was trying to find comets, but instead he was finding all these little blurry objects that look like comets, but they weren't exactly it. And so he was getting super frustrated. He would write down like, oh, this object is not a comet. And he'd be like M1 and then M2. And that's how we got the Messier catalog. And so here is our blue Snowball nebula. So the blue Snowball nebula is in the constellation Andromeda. And so we don't really know the distance to this nebula. It doesn't really have accuracy. We assume it's about 1,800 light years away, but it's a very huge nebula. The diameter is about 20,000 astronomical units. And so 1 AU is around the distance from the sun to the earth. So think about that times 20,000. So it's a very, very wide object. And I think this one looks super cool just because you can actually see the ring around it. And then you can kind of see these jets coming out from either end. And so some planetary nebulas have these jets, others don't. We're still trying to better understand planetary nebula. Studies that show they aren't actually as spherical as we think. Sometimes they come out towards the different poles. Sometimes they come out towards the equator. So we have lots of different variation in the shapes, quadrupolar. Sometimes we have bipolar planetary nebulas. So that's why I kind of wanted to show you these different variations that we can get in these objects. And so again, right in the center of this one, you can see the little tiny white dwarf there, the core of the dead star. Okay, so let's go to another one. This one's going to look a little bit similar. Let's go to the Saturn Nebula, so NGC 7009. And so the Saturn Nebula kind of sounds tricky. It's called the Saturn Nebula, but it has nothing to do with Saturn. It just kind of looks like it. And so the reason why it's called the Saturn Nebula is because this one's actually a bipolar nebula. And so it has a variation of different things going on. It has a halo, it has jet-like streams, it has different shells, it has handles, filaments, knots, and so all these different things kind of give the Saturn Nebula its shape, just like the blue Snowball. And so it looks very, very similar and has a nice bright blue color. And again, right in the center, we can see the white dwarf. And so yeah, someone, I think, assumed it looked like Saturn just because of that. So that's why we got that name. But you can really see here when Sarah brought down that exposure, the really, really pretty structure of this object. Okay, so we got a question from Ed. Do all nebulas have conditions for starbirths? That's a very good question. So when there's different types of nebulas that are out there. So the nebulas that we're talking about right now are planetary nebulas, and they form when stars die. But there's other types of nebulas that stars are born in. So yeah, while we're at it, let's go to a star-forming region. Let's go to the Eagle Nebula. And so the Eagle Nebula is this big plain of gas and dust where stars are born. And so while we wait for it to go there, yeah, there's different types of nebulas. There's emission nebulas, there's dark nebulas, there's stellar nurseries, planetary nebulas. And so these gases that form in planetary nebulas, eventually, it goes out into the galaxy and it could coalesce and eventually could potentially create conditions for a star to be born. But we do know that all stars are born from gas and dust. So stars exploding and creating all this gas and dust in itself is the whole reason why we have more stars being born all the time. So it's this kind of never-ending cycle. So although these planetary nebulas won't necessarily form another star, it could make the conditions eventually throughout the galaxy to create other stars, just like in this region. So here we have the Eagle Nebula. And so we can see the really red colors coming out from the top left there. Those are actually called the pillars of creation. So if you guys know that very popular Hubble image, the pillars of creation, this is it just kind of flipped around. And so inside the Eagle Nebula, or the pillars of creation, is baby stars being formed. And so these baby stars, they're having tantrums. They're very violent. They're whining a bunch. And so they create something called stellar wind. And this stellar wind from these baby stars is super strong. So it's blowing out and pushing out that gas and dust. And so we get these really elongated shapes, which are the pillars of creation. And so we have a question from Daniel asking, why is the Eagle Nebula called so? I believe the Eagle Nebula is called the Eagle Nebula just because someone interpreted it looking like an eagle. So you can kind of see, the eagle shape that Sarah is drawing out there. Again, a lot of these objects are named after someone interpreting it looking a certain way. It doesn't necessarily have to have a scientific reasoning behind it. Yeah, see, there's our cute little eagle right there. And then the pillars of creation, I believe the pillars of creation were called that because they're creating baby stars, and they're these enormous pillars. And so again, that's where baby stars are formed, the stellar nursery. Okay, and so just going to loop around real quick back to planetary nebulas. We're going to look at two more planetary nebulas, the most popular ones in the sky. So let's go to the Ring Nebula. And so I would say the Ring Nebula is probably the most infamous or the most famous planetary nebula in the sky, just because of how pretty the colors are and how easily accessible it is to amateur astronomers. And so the Ring Nebula is in the constellation Lyra, and it's fairly bright. So even with a small telescope or even binoculars, like really strong binoculars, you should be able to find this object fairly easily. And as you can see, this one's just the picture perfect definition of a planetary nebula. It's round, we got the pretty colors, and we have the white dwarf right in the center. And again, the colors in the Ring Nebula are because of ionized helium, that's the blue color. The cyan color is kind of the hydrogen and oxygen, the inner ring. And the red color is from nitrogen and sulfur from its host star before it died. And so I was kind of mentioning a little bit earlier how there's new studies to show that planetary nebulas don't necessarily have to be circular. And so with the Ring Nebula, one theory is that we're actually looking kind of down into a cylindrical shape that was formed when this star died. And so we actually have another perfect view of this kind of looking sideways at the cylindrical shape instead of down into it. And this one's called the Dumbbell Nebula. And so if we want to head over to the Dumbbell Nebula real quick, this one is just kind of showing you what it looks like from a different angle. But again, with all the different planetary nebulas that we saw, we can see that they form all different sizes and shapes and colors and features. There really isn't a surefire way that these stars die and the shape that they're going to form. And so the picture is kind of loading up there. And something else I want to mention, that when Sarah moves the camera, sometimes you'll see streaks on the screen. That isn't a shooting star. It's not a satellite. Occasionally you might see a satellite passing through, but what's happening is she's taking an exposure while the camera moves, so the stars are streaking across the field there. So it looks like shooting stars and it looks like satellites, but it's just actually a component to our camera moving. So you can see the pretty colors in the Dumbbell Nebula. And you can really see that shape there and why it's called the Dumbbell Nebula. We kind of got those two handles there, and you can see a lot of structure on the inside as well. So this planetary nebula is a lot closer to us, and it's a lot bigger too. So that's why we can really see the structure. And again, the little white dwarf in the center. So those are all the planetary nebulas that I had in store for tonight. Just kind of giving you a view of a lot of the objects that we have up in the sky, the planetary nebulas. There's quite a few up in the sky tonight. And later on, we'll look at some other ways that stars die. But for now, let's go look at some stars and see what some of these stars look like before they hit that planetary nebula stage. So let's go to Altair. And so I'm going to be looking at 3 stars that are in an asterism called the Summer Triangle. And so we have 3 stars in the summer triangle. We have Altair in Aquila, we have Deneb in Cygnus, and then we have Vega in Lyra. And so I thought we would look at the summer triangle one more time before we completely lose it and go into the fall and winter months here. And so we have Altair right there, that bright little dot right in the center. That is our star Altair. And so Altair is only 16.8 light years away from Earth. So it's one of our closest stellar neighbors. And Altair is rotating really, really fast. It only needs 10 hours to spin on its axis compared to the sun, which needs around a month to spin on its axis. And so we know Altair will become a planetary nebula just based on its mass. So Altair is 1.79 solar masses. And so we know that under 3 solar masses, these stars form planetary nebulas. And so that's why we know this one will form into a planetary nebula. All right, so let's go to Vega. So Vega is a little bit more on the iffy side when it comes to the formation of planetary nebulas. A little bit about Vega itself. It's the brightest star in Lyra, and it's around 25 light years away. And it's a very important star that's been studied extensively by astronomers because it was our North Star at one point, and it will be again in the future. And so around 12,000 BC, Vega was the North Star, and it will be again in the year 13,727. And the reason why that is because the Earth is actually wobbling a little bit on its axis. And so the Earth's kind of pointed this way, and so in its wobble, the axis will kind of move around in the sky. So right now, the North Pole is pointing at Polaris, but eventually it will kind of move around and it's going to loop back around to Vega. And so Vega's mass is 2.6 solar masses, so it's a little bit heavier of a star. It's just right at that threshold. And so there's 2 possibilities that can happen with Vega. It could turn into a planetary nebula. It could just kind of stop that nuclear reaction, or it could potentially explode into this huge explosion called a supernova. And so we'll look at one more star in the summer triangle. We'll look at Deneb. And so Deneb, we know for sure, is going to go supernova because it's a massive star. And so Deneb is a blue-white supergiant, and it's around 2,616 light years away. So compared to those other stars, they look super bright, but they are a lot closer to us compared to Deneb, where it's super far from us, but it's still really, really bright. And that's just because of how massive it is and how much light it's emitting. And so Deneb will eventually collapse upon itself, explode, form a supernova explosion, and then potentially create a black hole or a neutron star at the center of where the star was. And so that's what I like, the kind of variation we have in the summer triangle, where we have the smaller stars, the ones that are closer to us, and then the larger ones, the ones that are going to go out with a bang. Okay, so I think we have some recommendations right now. So let's go to Andromeda. So that's the first request that we got. And so the Andromeda galaxy is the closest galaxy to us. And it's really big in the sky. So when it appears on the screen, it's going to look really, really bright and really close up. And so actually, the Andromeda galaxy is very large in our sky, but it's so dim we actually can't see it all. And that bright part that we can see is the core of the galaxy. So we can actually see the Andromeda galaxy with our naked eye, but it's just the core, and you have to kind of know exactly where to look. But this is our twin, this is our sister galaxy. It's another spiral galaxy. And so maybe we can bring up the exposure just a little bit. Yeah, right there, perfect. And you can actually see some of the dust lanes in this galaxy. And so just like the Milky Way galaxy, the Andromeda has arms, it has its own structure, it has stars that are being born in it. And so in that kind of darker region, that's where the stars are being born in the galaxy. Compared to the core of the galaxy, there really isn't a lot of stars that are being born. Towards the center of galaxies, that's where we get our old stars, that's where we get a lot of interaction. The stars that are dying and that live a really long time kind of just orbit around the black hole in the center. And then in those dust lanes, those darker parts of the galaxy, that's where all that star forming activity is happening. That's where we get all the planetary nebulas, all the supernova explosions, exoplanets, other solar systems, and stuff like that. That's where all that activity is happening, all that younger stuff out in the arms of Andromeda. Okay, so let's see. We have another request. We have the Perseus double cluster. So let's go to that one. So the Perseus double cluster is in the constellation Perseus, and it's called the double cluster just because there's two open clusters next to one another. And so we have two of them, and this is a little bit different object. It's a younger object called an open cluster, and these are formed when stars, a little bit bright there. These are formed when all the stars in those star-forming regions in the stellar nurseries are formed. They eat up all that gas, and then they create these open clusters. So we generally know these objects to be younger stars, but it looks like this object, unfortunately, is in the roof. It looks like it'll rise maybe a little bit later. So instead, we're going to go to M11. Or actually, Sarah, do you mind? We could do the owl cluster. I had the owl cluster written down. Yeah, so we might be, owl. Let me see what the number is real quick. So the owl cluster is NGC 457. And so, this is a little bit different from the Perseus double cluster, but it's kind of in the same region. It's in Cassiopeia. And so I like the owl cluster just because it looks like an owl. We're not going to get the full shape of the owl here. Oh, actually, we are. That's cool. So once the image settles a little bit, we will be able to make out the shape of an owl. And so those two bright stars to the top left are the eyes of the owl. And then we kind of got, if you use your imagination, you can kind of see some wings, and then the two stars kind of to the center bottom are the feet. I like this one just because you can actually see the shape that it's named after. And so again, these open clusters are younger stars. This one's about 7,900 light years away from the sun, and this one's around 21 million years old. So it's not... it sounds old, but it's very, very young in astronomical terms. And so there's Sarah drawing that beautiful, beautiful owl shape of our cluster. Yeah, I like this one. I think this one looks great through an eyepiece, especially through our TEC telescope. I like how this one looks. Okay, cool. And if you want, we can go back to the wild duck cluster as well. And so we'll see another open cluster, just kind of get them all crushed out at once. So the wild duck cluster is kind of in the region of Sagittarius. And so again, this one is actually in the lane of the Milky Way galaxy. And so tonight we actually have the Milky Way galaxy up, and we have a bunch of objects that are in there. The Eagle Nebula was in there. We have the lagoon, we have Trifid, and then we have the wild duck. And so in the lane of the Milky Way galaxy, where all the arms are, that's where a lot of that star-forming region is. That's where a lot of that gas and dust is. And so we get these young stars being formed. And so the wild duck cluster is called the wild duck because there is this V formation in there that resembles flocking ducks. But it's a little harder to make out this V. I kind of see it. But that is our wild duck cluster. Okay, I think we have, let's see, another request. So let's do some planets. So first off, let's start with Mars. And so again, this upcoming month is the Mars opposition. So we will be having live streams covering the history of Mars, observations, recent research, and that will be happening all this month on Tuesday. So tune into those at 8 p.m. And so I love the view that we can get of Mars right now. We can actually see a lot of features on the surface, which is really interesting because usually we're not able to do that. And so right here you can see we have some darker regions on Mars. So that is a lot of basalt or volcanic rock that's on the surface. The lighter regions are dust and stuff like that. And then just to the very top left, maybe 7, 8 o'clock, we actually have a polar cap. And so Mars has 2 polar caps, and they're made of carbon dioxide ice and water ice. And so it has a north polar cap and a south polar cap. You can kind of see it, but we have a lot of detail tonight in Mars. And so as it gets closer and closer in its orbit, we're going to be able to see maybe some more structure and detail. We have a request for Venus, but unfortunately Venus is not up right now. So we are pretty lucky as we have a lot of planets in the sky right now. We have Venus, we have Uranus, we have Neptune, Jupiter, Saturn, Pluto, but we don't have Venus and Mercury. So the reason why we don't have Venus and Mercury is because they orbit so close to the sun that we actually only see them during certain parts of the year. And so we actually had Venus up in the sky for a really long time, around spring, winter time. And Mercury, it's really difficult to actually observe that one at night. So I don't think we ever actually see that one at night because it orbits so close to the sun. But we did have a transit of Mercury that happened not too long ago. I believe it was in November or something like that. And that was when Mercury transited in front of the sun, and so we could actually see it just kind of across the sun. And so, Venus is visible in the early morning though. So if you are willing to get up around 4 a.m., 5 a.m., you should be able to see a very, very bright star just before the sun rises, and that is Venus. And so I say it looks like a star because it's super bright. People have no idea what it is. Sometimes I even think it looks like a plane or a helicopter, but it's Venus. Okay, so let's look at some of the other planets while we're at it. So let's look at Jupiter. So Jupiter is getting pretty low in the sky. Jupiter will be setting earlier and earlier now, but we can see some moons with Jupiter tonight as well, and we should be able to see the red spot. I thought that it will be in the plane of view, so we will see. And then we have a question. What is the name of the software being used? We are using the Malancan Sky software right now. And so this comes with our Malancan camera, and it's just the software that comes with it, so we can get these exposures. So here we have Jupiter, and right there is the Great Red Spot. And so you can see a lot of the different stripes on Jupiter. So those are the different atmospheric layers. And so Jupiter is a little bit of a different planet. It is actually made of gas. I know we've been talking a lot about gas, and that's because there's a lot of gas in our galaxy. And so Jupiter does not have a surface. We actually can't go to the surface of Jupiter because we'll be crushed by all the pressure that gas is forming to even make a planet. And so all this gas has different layers that it kind of settles in. And so we have darker bands, we have lighter bands, and that's kind of the heavier and the lighter gas that's kind of settling in those different areas there. And so if we turn the exposure up a lot, we can actually see the moons of Jupiter. And so the 4 moons that you should be able to see, actually, I believe one is transiting Jupiter. So I think that's why we can't see it. But the 4 moons you should be able to see with Jupiter are Callisto, Ganymede, Europa, and Io. And those are the 4 Galilean moons. And Galileo is the one who first observed those. That's why they're called the Galilean moons. But also, they're just so large. Ganymede, the largest moon of Jupiter and is the largest moon in the solar system, is actually bigger than our own planet, Mercury. So They're really, really big moons around the same size, even bigger than Mercury. And that's the reason why they look so bright, is that they just have a lot of surface to reflect all of that sunlight back at us. And so I believe the order that the moons are in is Callisto is that lone one on the top. And then we have Io transiting. And then to the bottom, we have Ganymede and then Europa. So I believe those are the orders of the moons right now, but they change all the time. They're orbiting, and like I said, Io's transiting in front of Jupiter. So maybe, another hour or two, Io will pass by Jupiter, and then we'll be able to see it again. And so that's what's fun about observing Jupiter, is you can look at it at different times of the night, and you can actually see the moons moving around. So I think that's super cool. And yeah, there's our Jupiter there. It looks great. Okay. Let's see. I have some other questions that I missed from earlier. What year did we lose the North Star? So we didn't ever lose the North Star. We actually still have a North Star right now, Polaris. It's going to be our North Star for quite a while. I don't know exactly when the tilt will kind of wander around and we'll lose it. But it's going to be quite a while from now. And again, those stars don't ever actually go away. The orbit just kind of moves around, or the wobble just kind of moves around. And that's why it's in a different position. Another question we have, what is the difference between open clusters and globular clusters? Well, that's a great question. So let's go to a globular cluster. Let's go to, let's go to M13, I believe. Let's see real quick here. Yeah, M13 is the Hercules cluster. And so we have M13 here. Its distance is around 22,000 light years away. So it's a far object. And the difference between this globular cluster compared to the other clusters that we saw, open clusters, is that these ones are a lot older. So this particular cluster is 11.6 billion years old. And just to give you kind of a time scale, so those other ones was like 21 million years old. This one's 11 billion years old. And then our own galaxy is 13.6 billion years old. So these objects are basically the same age as our own galaxy. And so there is some theories behind that. One theory right now is that these globular clusters actually did not form in our galaxy, that they were their own little galaxies that just so happened to pass by the Milky Way in its orbit in the whole entire universe. And the Milky Way decided to capture it and make it its friend. And so ever since then, it's been orbiting around the center of our galaxy. And so we have lots of globular clusters orbiting around our galaxy. They orbit around the halo of our galaxy. So they orbit a lot farther than the disk of our galaxy, where the spiral arms are. They orbit kind of around that plane there. But so these are very, very old objects. And so that's basically the difference, is that these ones are older, probably didn't form in our own galaxy, were swallowed up by ours, compared to open clusters, which were formed in our own galaxy, were formed from gas and dust, and they're just young baby stars. All right, let's see. Okay, we have a question asking, can Lowell use bigger telescopes for interactive stargazing? So a lot of the bigger telescopes that Lowell has are actually research grade telescopes. So the research telescopes that we have are the LDT, the Lowell Discovery Telescope. We also have our Anderson, or the NPOI telescope, the Naval Precision Optical Interferometer. We have a lot of partnerships with other larger telescopes. The thing is, those are reserved times for astronomers to do their research and take data. The largest telescopes that we have on campus, we have our 32-inch, 32-inch star structure telescope. That's what it's called. And that one is a little bit slower. It really wouldn't do well with the camera hooked up to the back of it. Just the plane waves move so fast that it allows us to go to these objects super quick and see them. Potentially, these larger telescopes could have cameras hooked up to the back of them, but they really aren't optimal for these programs that we do. But if anyone has any other final requests or questions, please feel free to put them in the chat right now, and so we can get to them. But let's see some other objects. Let's go to Saturn. So we have a few more objects in the sky, or other planets that I want to look at, like the moon and Saturn. So yeah, I think Saturn is really cool. Saturn is kind of like the tear-jerking planet. It just looks so pretty. You've got the rings. We actually have some moons around Saturn. These ones are a little bit more difficult to see. You can actually see them. So you can see the little specks around Saturn. Those are all of Saturn's moons. So Saturn actually just recently won first place on having the most moons in the solar system. So I think Saturn now has around 83 moons, while Jupiter's just slowly lagging behind with 76. But again, we keep finding new moons, so I guess we'll see who wins that competition. So that is Saturn and its moons. We also have a request for Uranus and Neptune, and those we should be able to see. So let's go to Uranus. Uranus is a little bit closer to the moon, so I guess we'll see how it looks. Oh, it's actually a little bit lower. Yeah, we'll see how Uranus looks. Oh, there it is. And so Uranus and Neptune, they're very, very far away. I believe Uranus is around 1.7 billion miles away, and Neptune is a little bit further than that. And so when we see them, they just look like little specks, little points of light through the telescope. We won't be able to see any detail, won't be able to see any moons, but it's still cool that we're able to see these planets super far away. And so there is Uranus, and you can kind of see the slight color to it, but we actually have a lot of, it looks like, atmospheric turbulence. And so all that means is that there's just a lot of atmosphere that light is passing through, so it kind of gets a little murky. You know, we have smoke and stuff. But let's try, so it looks like we can't get Neptune just because it's so close to the moon. We can try, but it might be washed out just because of how close it is to the moon. And then after Neptune, let's look at the moon. And so right now we have a very, very big, bright moon in the sky. So it makes it just a little bit more difficult to see these deep space objects. But again, since we have these exposures, we can still get somewhat of an image. And so here is Neptune. It's a little bit better. You can still see a little bit more of that blue color around Neptune. Yeah, so there is Neptune. All right, let's see what else we have. Oh, so yeah, you actually can see Neptune's moon Triton right there. And so Triton, we believe, was a friend of Pluto's at one point. There is evidence that shows that Triton was a Kuiper Belt object that was kicked out of its orbit and was pushed towards the solar system, and that it passed so close by Neptune that Neptune decided to grab it and make it one of its friends. And so the reason why we think that is just because Neptune or Triton orbits completely opposite of all the other moons, and based on physics and formation theory and stuff like that, in retrospect, if it was formed around Neptune, it would be going the same way, but because it's going the opposite, we think that it was captured. And so there's a Neptune. Let's see. Let's try the Veil Nebula. So instead of going to the regular Veil Nebula, let's try the other parts of the Veil. We have NGC 6995, I think, or 6960, whichever one of those. So the Veil Nebula is a supernova remnant. So earlier we were talking about planetary nebulas, we were talking about stars dying, and that these smaller stars, when they die, they don't go out with a bang, they fizzle out. But the big stars, those are the ones that explode. Those are the ones that go out with a bang. And so the Veil Nebula is a remnant of one of those stars that went out with a big bang. And so this is part of a thing that we call the Cygnus loop, since the Veil Nebula is in the constellation Cygnus. And we believe that this supernova was a star was a star that was 20 times more massive than the sun, and it exploded probably 10 to 20,000 years ago. And so the Veil Nebula is this massive, massive part of the sky. And so there's these tiny regions in the Veil Nebula that people have identified and called different nicknames. It's a little bit difficult to see this one right now just because of the bright moon, but you can kind of see some structure going on. We have some different colors. We have some pink and red colors, and we have some blue. And again, that's just the different gases that were kicked out of the star when it exploded with a bang. And so this part of the Veil Nebula, I believe, is called the bat wing, but I think it looks like a hand going like this. And then Sarah thinks it looks like a spider. And so, yeah, I think all parts of the Veil Nebula look amazing. And there's another part of the Veil Nebula we can see if we can try to get. It's NGC 6960. This one's called the Witch's Broom. And so again, it just has a lot of nebulosity going on, lots of different colors. And that's all because of stars exploding. And that's the whole reason why we have all the elements here on Earth, is because of the intense amount of energy that happens when these stars explode. We get elements crashing into one another and forming heavier ones. And so that's why we have everything that we have here on Earth, because of stars exploding. And so you can see there's a bright star in the middle there. I don't know exactly what star that is. I believe it's a star that is around Cygnus, but it makes it a little harder to see some of the nebulosity in the Veil Nebula, but you can still see there's some red and there's some blue kind of spirals going out there. Let's see, some questions. Which one in reference to which part of the Veil Nebula? So right now we're looking at 6960, the Witch's Broom. They're all different parts. I don't know exactly where they lie in the Cygnus loop. Again, it's this huge, huge structure of gas. And so all these little tiny parts in that structure have their own tiny little names. Another question that we have from before, shouldn't the particles in the Saturn's rings be considered as moons? If so, Saturn will be having millions of moons. That's actually a really good question. So the rings of Saturn are just labeled as the rings of Saturn. They're not considered moons. I believe there is a certain criteria for something to be considered a moon. I believe it has to have more of a spherical shape. It has to have some type of, gravitational interaction with the planet. And so the rings, I think all those objects in the rings aren't considered moons. They're just considered parts of the rings. But that would be something. If all the particles in there were called moons, then it would have lots of moons for sure. But what is interesting actually about that point, though, is that we do think the rings were originally a moon, and that moon just got close enough to Saturn to be tidally ripped apart. So it got so close that the gravity of Saturn just kind of pulled the whole entire moon apart and strung it across, and then we got those rings. And so that's also a good analogy for what happens with the solar system and how the solar system formed. And so there's all this gas and dust when the star collapsed, and it flung out all this material into a disk. And that's why we have all the planets kind of orbiting in this nice plane, because of that accumulation that happened when the solar system formed. And then the same thing will happen with Saturn's rings. All that material will accumulate, and it will make another moon or several moons, and those moons may collide with one another, never ending, and then they might get tidally ripped apart again. So yeah, very cool. We don't think the rings of Saturn were very long or a very old feature. We think they happened fairly recently, like maybe around the dinosaurs' time. We think if the dinosaurs had telescopes, they wouldn't be able to see any rings because it happened so recently. And then we think that it won't last a long time, that it will, accumulate and make moons. So it's not going to be a very long lasting object. All right, let's see what else we have. So we have a request for the Horsehead Nebula. So unfortunately, the Horsehead Nebula is in the constellation Orion, and Orion is a winter constellation. So it's not up right now. If you are a night owl like me and you're up at midnight, 1 a.m., Orion will be up, and then you'll be able to see it then. But come back in a few months, and Orion will be up around this time, and then we'll be able to view the Horsehead Nebula. And then we have another request for the pinwheel, M33. Is that the one in Triangulum or the one in Ursa Major? So we have kind of two pinwheel galaxies, Triangulum. Yeah, sure, let's try Triangulum. Yeah, so pinwheel, the name pinwheel sometimes refers to two different galaxies. We have one in Ursa Major, that's the actual pinwheel. And then the one in Triangulum sometimes gets called pinwheel just because it looks very similar, but it's in the constellation Triangulum. So yeah, so let's see how this one looks. I don't know, just because it's a little bit closer to the moon and it is very, very faint. I don't know how this object will look, but we can take a shot. Oh yeah, we have something else that we may be able to look at, which is NGC 891. And so I think this one will be our final object to look at. And so we'll see how Triangulum looks. It looks like it is very faint there, a little bit harder to see. Unfortunately, we'll give it a few more seconds, see if we can get anything. But so the Triangulum galaxy is another galaxy that is fairly close to the Milky Way. It is in our local group. And so, oh yeah, you can see the structure of the Triangulum galaxy here. So again, the brightest part that we can see with our eyes is the core of the galaxy. And you can barely kind of see some of the arms. It's another spiral galaxy where all that star-forming regions are, where all that gas, where all that dust is. And then in the center is where our supermassive black hole lies. Oh, okay. So yeah, so let's try, after this, let's go to NGC 891. And so it's another galaxy. This one's more of an edge-on galaxy, I believe. It's another spiral galaxy as well. And so we'll see how this one looks. Oh, it might be, yeah, we'll just see how it looks. But there is different views that we can get of these spiral galaxies. So this one, the Triangulum one, we call it face-on, compared to 891, which I believe is an edge-on galaxy. And so we're kind of looking at it completely edge-on compared to face-on, like that. And you can see some of the other structures, like the halo, when we do get the edge-on one. So yeah, right there. So you can see very well, you can see the disk of the galaxy, and you can see that dust and how thick it is. It's blocking out that bright, bright core. And then that kind of bulge around the core, that's called the central bulge. And that's where the halo is. That's where those globular clusters orbit and stuff like that. And so this is a very, very pretty edge-on galaxy that we have right now. All right, and so with that, let's go to the moon. And so again, as I mentioned, we have a very, very bright moon out right now, so it does make it a little bit more difficult to see these deep space objects. But with that, the moon looks great, and it's super cool, and it's our moon. It's our closest satellite. And so a little fact about the moon, we have had the Apollo missions at Lowell. We did lunar mapping for the Apollo missions. So with the historic Clark refractor, before we actually went to the moon, we had to see what the moon looked like and map out where they were gonna go and stuff like that. And so a lot of moon mappers actually came to Lowell and mapped out the moon. And so that's some things that we have done with the moon here at Lowell. Also, you can see some really cool features right now. You can see those dark spots. That is the Maria on the moon, or the mare. And so I believe that's Latin for lakes or oceans. So a long time ago, before they had telescopes, they actually thought these regions were oceans or bodies of water. So they called them Maria. And now we actually know that they are volcanic rock. And so we do believe that the moon was formed from the Earth, and the moon, being a terrestrial rocky body, it had volcanic activity at one point, and it had volcanoes, and we had objects hitting the moon that was creating molten rock on the surface. There's mountain ranges on the moon, but a lot of those are still formed from impact craters. And you can see that On our side of the moon that we can see, we have these really big spots, but generally there really isn't a lot of activity compared to the other side of the moon. So unfortunately, we don't have a view of the other side of the moon right now. But the other side of the moon has all these craters, all these spots all over the surface compared to, look at the Maria, where it's very, very smooth. We don't have a lot of craters. And that's because the moon is tidally locked with the Earth. And so we have one side constantly facing us, and the Earth is protecting the moon in that way compared to the other side, where all these other objects are allowed to hit the moon and kind of pummel its surface with all these different craters. And so the moon actually does rotate. So unlike the Pink Floyd album, Dark Side of the Moon, there is a dark side occasionally of the moon, and that's called nighttime. The moon does orbit, and the moon gets equal amounts of light. So there isn't a permanent dark side of the moon. It has an orbit. It rotates every 27 days, so around a month. And that's why every month we have the different phases of the moons. And so every part receives equal amount of sunlight. And so the dark side of the moon is just nighttime. And then the light part is daytime. And then right at the top right corner, we have something called the terminator. And that is where it is sunrise or sunset on the moon. And then we can see some really, really bright craters. We have Tycho crater. We have Galileo. I don't know necessarily exactly which ones are which. I believe the brightest one is Tycho. But you can just see some of that variation of the color on the moon. The moon isn't just black and white. It looks black and white to us, but when we actually go to the moon and we actually see it, the moon is all these different colors. There's blues, there's greens, there's yellows. So the moon actually has a wide variety of colors. And a lot of that research is done at ASU and U of A with the LROC camera, with the Lunar Reconnaissance Orbiting Camera, something like that. So a lot of that research is done here in Arizona, currently, of the moon. Okay, so I believe that is all that we have for tonight. Again, I would like to emphasize the fact that we have the Mars opposition live streams happening this month. Please check those out. They're going to be super informational. We have a lot of guest speakers coming in to talk about the Mars opposition. As well, we also have the premium access experience. Definitely go to lowell.edu and check those out. We have all these awesome telescopes that are just waiting to be used. They haven't been used for such a long time, and they're just begging for people to look through them. And then you can personally come and see for yourself how the plane wave works, how the Malacam works, and take some pictures and have them for yourself. So definitely come over and visit us at Lowell Observatory. And thank you guys so much for tuning in tonight as well. And have a good night. And thank you so much for joining.